Cool. So let's get started. This is a bit of an agenda for what we're going to talk about today. I forgot to add one of the questions. It's going to be down here, so don't worry. There's going to be space for asking questions if necessary. But this is what I'm going to be covering today. I'm going to be talking a quick review of what computer architecture is, what you understand about it, what a computer is, real quick, just to brush up. I'm sure all you guys are familiar with it. And then you who know me know that I'm a very hands-on person, so I don't want to present a bunch of concepts to you just floating up in the air, but rather I want to put everything in the context of making a video game. So we're going to show some code about what an OOP C# solution to that problem would be, and then we're going to talk a bit about restructuring our data, making some comparisons, and then we're going to draw some conclusions from it. So you guys, I'm pretty sure you're all familiar with this already. This is the von Neumann computer model, or in English I've heard it pronounced as von Neumann. The idea is that a computer is just a CPU and a memory. That's what a computer is. And the idea was to introduce some sort of model to which we can make programs, right? Now, the problem that we have here in this model is that because of Moore's law, we know that CPUs are really, really fast. They're getting faster all the time until, well, recently where we hit a temperature bottleneck. But other than that, CPU speed has really increased through the time. And unfortunately, memory hasn't kept up with the speed. In concrete terms, we usually end up having either on our phones or our laptops or our desktop computers, a CPU that's way faster than the RAM that we have, right? So we have a very fast device talking to a pretty slow device, which would be the RAM, right? Another problem is that CPU and RAM are separate. They're different components, and they're not together in memory. They're not together in a chip. So this introduces some distance, and distance is latency. So whenever we look at it, the CPU is always going to be faster than the RAM, and this is a problem, right? So how do we solve this problem? Well, someone had the idea of saying, well, why don't we just take a little piece of that memory and we throw it right inside the CPU, and we use that effectively as a cache, right? So the idea is that the cache runs at the same speed as the CPU. It's actually part of the CPU, so CPU has register. Now it also has this cache. And then we have the slow memory far away from it, but the good thing is that every time we need to read something from RAM, instead of just using it and then writing it back to RAM, which would be a pretty slow round trip time, we just write it in the cache, we work off the cache directly, and then as we need more cache, or as we need to work on more data, we can effectively evict stuff we're not using from the cache. So this is stuff that I'm sure you're all familiar with, but just to make sure we're all on the same page right now. As multi-core CPUs came along, we started seeing that each CPU core gets its own level 1 cache. So if we have a quad-core CPU, each one of these 4 cores is going to have its own tiny piece of memory, specifically for the data that it needs to process. Then again, for whenever we need to share data between the different cores, say we have a multi-threaded program, they're working on the same data, because no CPU has access to some other CPU's cache. A level 2 cache was introduced where it's a second level of caching effectively that is a little bigger, and it's usually shared between all the cores. So the idea is each CPU has its own cache, but in order to be able to share this fast memory or data stored in this fast memory between different cores, we also have the L2 cache. Another optimization that the hardware has is whenever we need to go to RAM, again, super slow read. So what do we do? Well, CPU manufacturers make it so that the memory management unit never reads only information that we need, but actually tries to predict what other data we're going to need in the future. So say, for instance, I have a program, it needs to add 2 30-point numbers, right? So I'm doing A plus B. The CPU says, okay, I need to fetch A from memory so I can do the addition. So it goes to RAM, gets those 4 bytes, brings them into the cache. Now it needs to have B, so effectively you can put in a register and do the addition. So we'd also have to go again to the RAM and fetch that number, right? So you can see it's pretty slow. Every single piece of data we need, we're gonna go and do a round trip. So effectively, the way to address this issue is that the MMU is smart enough to say, no, I'm not just gonna read the data you're asking me, I'm actually gonna read 64 bytes around the data that you're asking me. So in the case of a float, which is only 32 bits, 4 bytes, I'm actually gonna read a bunch of floats. So hopefully if A and B are together in memory, when I read A, B is already gonna be loaded in the cache for free. CPUs are also pretty smart in terms of, or MMU rather, it is pretty smart in terms of not only does it bring me 64 bytes of the data that it thinks I'm gonna need, but it can also look at our code and understand that as we are doing a linear operation like walking through an array, it can deduce that, oh, you just read this memory address, and then the next one, and then the next one, and then the next one. So it can effectively start prefetching in the background the following contents of the array automatically for us while the CPU is busy doing work. So that is the concept of prefetching. It realizes that we're iterating on an array, that we're going forward, and it's gonna start preloading all that data in the cache before we actually need it. So super fast. All right, so that's it for architecture in general. So let's think about a concrete example for a data problem, a data-intensive problem. So I wanted to keep it simple, nothing super crazy in terms of computer vision or a lot of arrays. Let's just say we want to build a massive real-time PvP game. We have 2 armies that are fighting for control in the Middle Earth, and we're gonna have this requirement that each army has between 250 and 5,000 soldiers, right? So we're talking about between 500 and 10,000 soldiers potentially active in the game at any time. And we also have the requirement that this needs to run at 60 frames per second and on a phone, right? So how do we take on this problem? We know we have 2 players, each player has an army. So army already starts to sound like a noun. So we have an army. What is the army composed of? Well, I guess it's soldiers, right? So object-oriented programming is telling us, okay, let's just start by making a soldier class. Your soldier is gonna be the representation of the minimum unit that composes your army, and then your army is gonna be a list of soldiers, right? So, okay, we start with a object-oriented design, and we create a soldier class. Because we're working in Unity, we decided to make it a mono behavior, and we add a bunch of stuff that we feel that the soldier is gonna need. So in particular, we're trying to be smart, so we try to avoid complicated inheritance. We're just gonna have a unique type, which is an enum that determines, okay, this is a sword soldier, or this is an arrow throwing soldier, or an ogre, or what kind of soldier it is. And then we need to roll some stats, right? We need to know the soldier's health, so we know when it's dead, we know if it's damaged. You can have base attack, base defense. You can also have attack and defense modifiers too. If we have something like AoE magic or anything that can boost the soldier stat, we put it in there too. And then we have a property which is the speed at which the soldier effectively walks in a destination, right? So think about it this way. The army is not gonna be very useful if I can't send my soldiers anywhere. So what we're gonna do is effectively when the user clicks somewhere, taps somewhere on the map or clicks there, we're gonna take all the soldiers that are currently part of the selection and we're gonna set their destination. So we know that when we update the soldiers, they need to start walking at their given speed towards the destination, right? This is perfectly reasonable and this. Yeah, it's clear? Cool. What does the army manager look like? Assuming we build an army manager, we need someone that updates all those soldiers, right? They could, in theory, update themselves, but let's say, okay, now let's just put everything together into a nice army manager class, because otherwise the other one would be too bloated, so that's bad OP. And yeah, as you guys can see, it's pretty simple. When a soldier is created by the game, they just let us know about it, kind of like a notification or an observer pattern. We store it in a list of soldiers, and then we have an update function. This could be a manual behavior or not, it doesn't really matter at this point. And what we do is when we're updating the positions, we walk the list of soldiers, we calculate the movement vector, which is, okay, where I'm going minus where I'm standing right now. We normalize that, multiply by the speed, and add it to the position, right? So this effectively makes it work. Some of you might already realize, oh, hey, you forgot to multiply by the delta t. That's true. This will totally change depending on the frame rate. It's okay. We're trying to keep things a little simpler. But in real life, we would also multiply by that thing. So we want to measure this. And we're going to measure it in a couple of environments that are very reminiscent of what we have here in the studio. So I'm going to test two configurations. One is going to be this computer, which is a MacBook Pro, 15-inch. It has a quad-core Intel Core i7 CPU that runs at 2.6 gigahertz. It can turbo boost to 3.5, which is effectively for a single-threaded program. It can overclock that thread while the other cores are sleeping. 16 gigs of RAM at 2133 megahertz. So we can already see that whenever I'm turbo boosting, my RAM's clock is 36% slower than my CPU. So there's no way that the CPU is not going to wait for something that's almost 40% slower than it. And we have a cache, like we discussed. So in this case, it's a quad-core CPU. So we have 432 kilobytes of level 1 for each core. Because it's a pre-advanced CPU, we also have dedicated L2 cache for each one of these cores as well. So it's like an extension of DL1, but a little cheaper as opposed to having a bigger L1 cache. This one is 256K, and then we have effectively that one shared cache, which is 6 megs, pretty big, shared between all the cores. And then our cache line size, which is effectively how many bytes we read every time we go to RAM and we bring to cache, is 64 bytes. This is documented, this is known, it's data that the manufacturer gives us. And then the other device we're going to test is the iPhone 6, just as seen on my desk. It's an Apple A8 system on chip. It runs at 1.4 gigahertz, so way slower. Has 1 gig of RAM. We don't know how fast it's running because Apple doesn't tell us. Like most of what we know about the Apple system on chips is through reverse engineering the hardware. So we know it's 1 gig of RAM because we can see it in Xcode, but we don't know how fast it is. However, we can infer by comparing to equivalent Android devices that the RAM is probably in the low megahertz, right? In the low hundreds. And this is to save power. It's exclusively to save battery. So we have, for instance, some Android devices boast 2 gigahertz CPU, which is pretty fast, and it's way faster than what Apple's giving us in this processor. But then the RAM is effectively clocked at 200 megahertz, right? So we have a ratio of 10 to 1 in terms of CPU speed compared to RAM speed, which is crazy. And in terms of cache, it's a dual-core processor, so we got 264 kilobyte cache. Notice they're actually bigger than the ones we have on this computer. We have a 1 megabyte shared L2 cache and a level 3, 4 megabyte system on chip shared, which I don't know exactly what system on chip shared means. It's probably shared with the GPU somehow. And cache line size, unfortunately, we don't know this either, but it's probably 32 or 64 bytes as well. So, okay, we got our machines. We run the code that we developed, and in our synthetic benchmark, we run for 500, 1,000, 5,000, and 10,000 soldiers. We gather 500 samples for each one of these, and we take the average of all of those. This is running, again, on the Mac. The environment is Mono because C# is running in the Mono virtual machine. And this one is running through a Yellow CPP. So what can we see here? We can see that, okay, for 500 soldiers, in the case of the computer, we're at under one millisecond, which is all right, I guess. In the case of the phone, we're at 2 milliseconds, which is pretty high already, considering we're only moving the soldiers. We're not drawing them. We're not doing collision detection. We're not seeing if one soldier is attacking another one. We're just walking that array. And you can see that as we add more and more soldiers, performance seems to become worse and worse over time, up to the point where we reach 10,000 soldiers, we're barely doing 60 frames per second in our update loop, and the phone is no way. It's like gonna be a 60 frames per second game. So let's take a look a little bit at what problems we have with the code we developed. So we follow standard object-oriented practice, and the university tells us, or academy tells us, oh, this is exactly what you should be doing. So your code is fine. Well, as game developers, so we can look at that code and say, for instance, C, because we know the details about the C# compiler, we know that there's no inlining, right? The C# compiler doesn't do any inlining. It's very conservative. If it does inline something, it's a very rare occurrence. Actually, if you want inlining, you should probably do it yourself by copy pasting the code. The C# compiler doesn't do it. So how many function calls do we have? Well, the answer is right there, but how many function calls do we have here in our update loop? Does it look like 7? The only parentheses we have are this, and it's because I messed up the Unity API. Actually, it is actually a property. So it shouldn't have parentheses. There's 7 function calls in here. They're all hidden in plain sight. Why? Because of the way we declare our soldier. If you remember, we did this. So we don't actually have access to the properties of the object. What we have are getters and setters. We have access on methods. And every time we call something with the dot notation, we're not actually reading a piece of memory. We're calling a function, right? In this case, we don't do anything, just get set. But these are function calls, and let's remember, there's no inlining. So the get will get compiled into a get function, and we're calling that function here. So if we count the number of dots that we have, each dot is a function call. So we have 1, 2, 3, 4, 5, 6, 7 function calls. Right? And that is every frame. So when we go back to our case of running at 60 frames per second, we're talking about 420 function calls every second. Completely free in the sense of we shouldn't be doing it, right? We're getting no advantage from doing this. We're just calling 420 functions every second to no end. Second problem, if you guys remember, we're doing a for each iteration over the array. Imagine we have only 1,000 soldiers, right? At 60 frames per second. Remember, every time I go and I move to the next element, I am effectively allocating a temporary iterator object. So at 60 frames per second, I'm allocating 60,000 tiny objects that the garbage collector is going to have to come and collect for me. No way, there's no deterministic destruction for reference types, so I'm going to have to come and delete this. Now, newer versions of the .NET runtime, like if you're on 4.6, take care of this. Unity has assured us. But you know, if you're using anything like value types in your array, and you're working over that using a for each, you are allocating this memory right now. And there's also boxing and unboxing, which is also it takes CPU time. It doesn't go away when it gets compiled. So I guess what I'm trying to say through this is that you may have a problem, or you might think that something is not perfect, but as soon as you crank up the performance to 60 frames per second, or you go to 60 hertz, something that was maybe a tiny issue, like, oh, I don't care if I'm allocating every frame, it's way, way worse, right? So, okay, we could go back to our code and fix these things. How do we get rid of the properties? Easy, we just make them public and we don't define any getters or setters. So we get rid of those 420 function calls. We can rewrite our for each loop to just be a plain old for loop with an integer counter, and that gets rid of all the function calls. And that would help. But here's the thing that we usually don't think about so much, and is, what does my memory look like? Right? And I think this is the most important part from this slide, at least. So let's take a look at the dumbest memory layout in the world. I made this myself, these graphics. Pretty proud of it. It's actually a table. And this is how memory works on a computer. It's obviously, even though we have stack and heap, we only have one memory in the computer. And stack begins at the top, and it grows downwards, and the heap begins at the bottom, and it grows upwards, right? So they would ideally meet in the middle, but hopefully that never happens. This would be the body of what the memory could look like in the body of our update loop, right? So you guys can see, okay, we have a game object that maybe holds the army manager. The army manager has a list of soldiers. Let's say we initialize that when we created the first soldier because we got our notification sent in. So we add the first soldier, maybe it's around there in memory. Then let's say when the soldier was created, came out of the barracks, a VFX was played. So that VFX was also nude and placed in memory, right? Now we have the soldier, and we have the VFX that it played. Maybe in the background we have some coroutine state that's also running. It's doing some work that has something to do with something else in the code, like waiting for a network response, waiting for an asset to download. But we have that coroutine state running there, and it's sitting in the heap. Then maybe we create another soldier, so that soldier is again nude and it's placed in there in the heap. Let's say that soldier, throws an arrow, so we also create that arrow and it's going to be sitting there in the heap. Then we create another soldier and it plays wherever it fits, right? So can anyone see a problem with this?
All over the place.
It's all over the place, right? Exactly. So when my update loop is going over this list of soldiers, it's actually jumping everywhere in memory. I'm coming to this soldier, then when the iterator increases, I'm jumping here in memory, then I'm jumping again because I need to avoid that arrow, right? So in terms of cache, this is pretty bad because remember, we're always reading 64 bytes because of the cache manipulation. So when I read this soldier, yeah, it comes into the cache, the full object, but then I get part of the VFX, which I don't really care about right now. All I care about is the next soldier, effectively. But I'm bringing part of that VFX. And worse, whenever I'm bringing in part of that VFX, because we only have like 32K or 64K of L1 cache, we're effectively evicting something else that was there that maybe I was using, so I can fit part of the VFX that I don't care about, right? We continue, we go to the next soldier. Again, it's somewhere else. So I need to go to RAM again and fetch that and bring it into my L1. I'm bringing part of the arrow with it, again, for no purpose because I'm not updating the arrows here. Then when I need to get the next soldier, well, sorry, it's far away, so again, I'm going to RAM, right? So it's a problem. So what can we do about it? Well, one thing we can do is we can force data to be together in memory. And this is something that C# lets us do. And it's something that would definitely help in this situation, right? As you guys know, classes in C# are reference types. It means that effectively they're a pointer to somewhere else in memory. But C# also gives us something called value types. And value types are types that are usually small. They live in the stack as opposed to the heap. They might be, well, in C++ you can allocate them wherever you want. In the case of C#, it doesn't matter right now, but value types have different semantics. In the case of references, what we have is a pointer to an object somewhere else in memory. In the case of a value type, what we're holding on to is the actual object itself. So if we have a struct, we know that that struct is binding all the data that it has inside it together into a single memory object. So knowing this, we can rewrite our soldier to be a plain old struct and get rid of the mono behavior, get rid of the class, get rid of all the getters and setters, so we avoid those 420 function calls. Because it's no longer a mono behavior, we don't have access to the transform, so what we're going to do is put it in there so we can effectively update its position as we update the soldiers. Again, transform is, in that case, because transforms are reference type, this is a pointer to the transform, which is somewhere else in memory. We don't really have a way to pick up the transform and just put it into this struct, but so we need to hold on to a pointer to it. But it's what we have. And now let's update the army manager to detect those changes. So what we're going to do is in the update function, get rid of the for each loop so we don't have those nested temporary allocations. And we're going to go, okay, a couple of things before. Notice that I changed from a list to an array. And the reason that I'm doing that is to also get rid of another assumption. And that assumption is that we can't assume anything, which is a false assumption. So for double negative, but here's the deal. When we declare that we can have a list of soldiers, we're effectively saying, I don't know how many soldiers I'm gonna have. So I might as well use a list, and I can jam as many objects as I want in there. But this is not entirely true. In practice, we know what the theoretical maximum number of soldiers our system supports is gonna be. We know from the TDD, or we know because we have performance benchmarks, or we have our budgets in terms of how many soldiers we're gonna draw. So we know this. We know we're gonna commit to maximum 1,024 soldiers, maximum 500, 5,000, 10,000, right? So we can allocate these beforehand and avoid doing allocations at runtime, which might actually make us have to go to the operating system and get more memory. We just allocate everything one big chunk and we keep it there in memory. And then what we're gonna do is we're gonna keep track of how many soldiers from that array are actually alive right now. Which one, how many from the potential maximum of 1,000 soldiers do I effectively have, right? Rest of the interface is the same. When a soldier is created, I just add it there. I need to make sure that we never create more than the maximum number of soldiers that we support. And then in the update function, we now iterate until from 0 to the number of soldiers. Get the soldier and do the same math we had before. So let's see how we did this time. Wow, we have only 3 function calls this time. It's way better. Down from 7. So 3 times 60, 180 function calls instead of 460. That's 61% fewer function calls, which is a huge win. We have no allocations. Everything is allocated beforehand. So effectively, 0 allocations times 6 is 0. And what does my memory look like now? Well, this is our memory layout. When we move away a little bit from object-oriented programming, we go into this stack memory layout. We still have our game object that holds the RB manager, but now notice this: we have the soldier array, and then we have all the soldiers that are forced to be together in memory. We pre-allocated all the soldiers, so they're all together, right? Granted, we allocated more than we need right now, but when the system is running at its peak and we have as many soldiers as possible for our game to sustain, we can guarantee that they're going to be held together in memory. Because every time we assign a soldier to this array, we're not actually storing a pointer to somewhere else in memory. We're copying the data that we need right in there. All right, so and how did we do now? We're gonna do, of course, we need to know. This is just me telling you stuff, but we need to see in the number if it's actually better. And here are the results. So very much to my surprise, the gains were, let's say, very humble at best. We can see that for the case of only 500 soldiers, yeah, we shaved about 20 milliseconds, 15 milliseconds, sorry, 0.15 milliseconds. And then the extreme case of 10,000 soldiers, it's a whole 0.3 milliseconds faster. So, yeah. That's a good. Now, the mono version, however, seems to be very, very good compared to what we had before. Notice that for the case of 10,000 soldiers, we just effectively reduce our compute time in about 3 milliseconds, which is huge. We see gains across the board for all the other values. This is the biggest one, and we're getting 3 millisecond performance gain just by restructuring our data. We didn't have to cut down on floating point accuracy. We didn't have to cut down on the number of soldiers, still 10,000. Our code is faster just by packing data differently. Is everything well now? Is this the end of the story? Well, the soldiers are together now, which is better. It means our cache situation is better. Every time we're reading a soldier in, we get part of the next soldier that's sitting next to it. And as we walk through this array, prefetch should be helping us bring the next soldiers in. But here's the thing. Remember, I keep on saying the cache line read is 64 bytes. How big is our soldier type? Well, we can calculate that because we declared it, and it's a struct. and we know the sizes of all the data types that we're storing in there. So we effectively have 8 fields plus 1 pointer, so 9 fields. All the fields we have, it's an enum and a bunch of floats. So these are 8 4-byte size fields in there, plus one 8-byte size pointer. So it's effectively 40 bytes. This is the size of our soldier memory. And here's a question. How many soldiers can we read from RAM as we traverse the array if they're 40 bytes? And I can read 64 bytes every time I go to RAM. I can read 1.6 soldiers, right? So that means every time I need to go to RAM and fetch a soldier, I'm reading that soldier that I need and about 60% of the next one, right? So I'm gonna have to go to RAM again if I wanna get the rest of the soldier as soon as I increase my counter and try to process the next one's position. And again, prefetching helps, but only 1.6 soldier is pretty low. We're gonna be going to RAM all the time. And now, can we make this any better? Well, we can, but it requires us doing away with the way we've been working so far. So you remember in the beginning of this session, I said, okay, let's take the object-oriented approach. Let's start with identifying the nouns in our problems. We identify an army, we identify a soldier, and we started modeling our program around that. But what if I told you we didn't have to go this way? What if I told you we can effectively just not focus so much on the nouns, but rather focus on the data that we need to process? If we go back to our soldier structure, we can identify 2 different kinds of data. Even though they're all in there together, we know that there's data that is hot, that we need to touch every frame, every time we're updating their positions. And there's data that's cool. There's data like how much life it has, what the base attack damage is, what the base defense is, what the soldier type is. This is stuff we don't care about when we're updating the soldier position. What we care about are where it's going, where it's standing right now, and how fast it can get there. So what we're gonna do for this attempt to make the situation a little better is we're gonna get rid of the idea of having a soldier, or at least in terms of updating the positions. And we're gonna define something that represents just a soldier's move, right? And soldier's move is a dumb name, but I need a name for the struct. It could be anything. What we care about is the data that we need to transform. So there's 2 ways we can pack this. We can make an array of structs. The structs bind the position, the destination, and the speed together. Or we could make a struct of arrays where we have a struct and each one of the elements is all the positions, all the destinations, and all the speeds. Because of the way C# works, this is the favorite approach because everything is kept together and the only indirection is the pointer to the array in memory. In the other case, we actually have 3 pointers into memory. So this is a way that Unity recommends we do this. And now we're gonna wrap this together into, again, army movement, another dumb name. I know this is pretty slow, pretty small, so I hope you guys can see, especially from the back, this will be available. It's exactly the same code we had before, but the difference is that we're holding on to the movements, we're holding on to the transforms in a separate array, and we're walking the active soldier list just like we did before, but this time we're only reading in the movement structure, doing the math with this, and assigning the position. And then we have a for loop at the end where we update all the transforms, okay? Why don't I keep the transforms inside the same structure? Well, each one of these transforms is gonna be an 8-byte wide pointer to somewhere else in memory. So by keeping it out of the struct, we're making sure that this data is even more packed. We don't have that pointer to somewhere else. These are the results for the mono version. We already knew that it was better on the computer than it was by just having the object-oriented approach. We can see that we can we shaved off another 2 milliseconds from our execution time. Again, we just restructured our data. We didn't decrease floating point accuracy. We didn't reduce the number of soldiers that we're updating. And we just changed the way our data looks in memory, and we get a performance increase for free. So how did we do on the phone? So from the previous chart, you know that the phone situation was pretty bad. It didn't make much of a difference packing the data together. But let's see how we did this time. Hey, that's starting to look better. So even though we were still fighting there, like saving 0.3 milliseconds, with this change, we have now shaved off 3 milliseconds from our update time. Again, same floating point precision, same number of soldiers. Why is this? Well, because because our data type is effectively smaller and everything is packed together in memory, we're making a better use of the cache. With our struct being smaller, we can fit more of the soldiers into the cache. Another way of looking at this is it's as if our cache was actually bigger, right? So packing the data this way allows us to see what, get the performance we'd get if our CPU had a bigger cache, even though it doesn't, right? And this is a big difference with maybe the competition. If they're not doing this, then it's not fair. We're gonna be developing for a better CPU, right? One with a bigger cache. So this concept I just introduced is, it has a name and it's called data-oriented design. The idea is that this is something separate from object-oriented programming, and it requires us to stop thinking about objects. Everything is modeled in terms of transformations of data. So the soldier move that we did, we only cared about modeling the data that needed to be transformed for that particular system. So you can think about updating all the soldier positions as a system. The system's responsibility is to update the soldier position in space. And we modeled our data accordingly. This means we got rid of all the data we didn't care about here, and we're gonna have to put it somewhere else. This is what I just said. Design the data that models the world and the processes that change it. We don't design around nouns anymore. We design around data. We focus on the implementation instead of the nouns. And the object that we used to have in our object-oriented approach doesn't really exist anymore, but we have all of its parts spread through systems that actually make sense for the CPU to process fast. So the object becomes just the sum of its parts. There's no soldier anywhere else, at least not for this, not for updating the positions. But if we put together all the pieces, then yeah, there's the object. And I think one of the biggest pillars of this theory is that we stop thinking about our programs executing in some theoretical machine, and we start thinking in terms of what hardware are we targeting. So you can see that as soon as I made the struct smaller, I'm making a better use of the cache. Why does it make sense compared to other optimizations? Because we know we're targeting a machine that has a CPU that's faster than the RAM, that has a cache that's trying to hide that latency, and that cache has a limited size. It's pretty small. So by coding around that, we're effectively tying our code to this specific machine, this specific von Neumann model with a cache, and not some theoretical machine that can process reason in terms of objects and do everything super fast and magical, right? There's no theoretical machine, for instance, that realizes, oh, I'm reading just the destination, so it's not gonna read the HP. No, the computer we're targeting, both the desktop and the mobile one, they can only read in terms of 64 bytes. So whenever we go reach that destination, we're putting in all the object. And the idea is that we consider the underlying machine and its properties all the time, right? What does this mean in particular? Reference. So again, super small. This is gonna be available. I stole this from Twitter. The reference is in the references section. But the idea is that not all CPU operations are created equal, right? The machines we're targeting have different latencies depending on what we're doing. So you can see a simple register operation like add or a binary OR operation. It's cheap, it's like one cycle. memory write, well, within the register is 1 cycle. Multiplication, we can see it's already between 1 and 7 cycles, so multiplying is more expensive, even though it's super fast than just doing an addition. Check it out, level one cache read, 4 cycles, super fast, still slow for what the CPU is, but it's super fast, I mean 4 cycles. Where is the main RAM read? Have you guys found it already? It's all the way down here, okay? So going to RAM between 100 and 150 cycles, right? That is equivalent of light going through a whale from the nose to the tip of the tail. Right? That's the distance light can travel in the time that it takes the CPU to get data from RAM. We compare to a 1, and a 1 is practically 3, right? Other interesting stuff in here, virtual function calls, we can see they're pretty expensive, between 30 and 60 cycles. Function call, 15 and 30. Wrong branch of the if statement, also known as branch misprediction. So I haven't really mentioned this, but it's important to stop and mention that there's actually 2 cache memories in each CPU. One is the data cache and one is the instruction cache. The idea of the instruction cache is to start prefetching the instructions that we're going to need to execute our program. Right? These need to be loaded into the CPU so the CPU knows what it needs to do. So instructions are also data in a sense, they go into their own cache. And prefetching tries to predict what the next instruction to execute is going to be, and that's called branch prediction. So if we have a function that has an if and an else statement, and 90% of the time I'm hitting the if body of the statement because the condition is true, the CPU realizes this and it can start prefetching those instructions every time I go into this function. Now, what happens in that odd case where actually the condition was false and I go into the else statement? Well, we pay for that. We pay for that in terms of the MMU having to go and fetch those instructions. 1,000 times we hit the right branch, the true branch of the if statement, the one that we do the false, we pay dearly. A last one that I want to call out, kernel call, down here between 1,000 and 1,500 cycles. What's a kernel call? What's a kernel call?
Reading a disk.
Read to disk. Yeah, what else?
Network card.
Yeah, network. So every time I'm checking if I have data on a socket, I'm paying that. You know, a print. If I print to the log, you know, I'm telling the operating system here, take this string, put it somewhere, right? So be careful with logging. Then exceptions are all the way down there. Don't do exceptions ever. Well, okay, so is everything well now? But we're still at 3 function calls, right? And we're still paying for those. So it'd be nice if we didn't have to do those. There's no inlining. So still, we're working on C#. The C# compiler won't do the inlining for us. This means every time we call a function, we're jumping there. There's no auto-vectorization. Are you guys familiar with the concept of auto-vectorization or vectorized instructions? So the idea is that a case that comes up very, very often is I'm working an array of floats and I need to process those floats somehow. One thing that the CPUs have is called multimedia extension instructions, and these are effectively very wide registers, like 128-bit wide, and these allow us to process 4 floats at the same time. So say, imagine I have 2 arrays and I want to add each each position from one array to the equivalent element in the other one and put it into a 3rd array. The CPUs have instructions to make this go faster. We can actually do 4 at a given time, but we need to code this, right? In C++, we have compiler intrinsics that allow us to drive this process. And the compilers are usually smart enough to realize, oh, you're working on an array of floats, so I'm just gonna generate this code instead. But we don't have this because we're working in C#. And this is the part that really broke my heart when we were talking to Unity last week. IL to CPP does not help here. So we're talking to Unity, and I told him, I don't care that we don't do inlining or that the compiler doesn't do automatic auto-vectorization because everything gets compiled to C++, and the C++ compiler is very smart, so it will realize that surely that I'm walking through this array or that I'm calling a function, and it will make will spit out great assembly code? And the answer I got from Unity is, well, actually no, because IL2CPP is pretty awful C++ code. It's all written in terms of gotos. C++ has goto, if you guys didn't know that. So there's no loops, there's no function calls, everything is goto everywhere. So the compiler can't reason about that code. The compiler optimizations are thought for the heuristics kick in when they recognize code that a human would write, not that a machine would write. So IL2CPP doesn't help at all. But the good news is that Unity is changing, and it's changing for good this time, and they're going to fix all these issues for 2018 and 2019. So there's a big internal push for what's effectively the new entity component system. The new entity component system replaces everything that is a mono behavior. Unity might actually even get rid of mono behaviors once they fully transition into this model. And the idea is that now whenever we declare a component, the component is no longer this bag of logic and data, but it's actually just data. And then we define systems that operate into this data. So what Unity's runtime can do is collect all the data from all these components, bring it together into an array, and our system is just processing that array. So it's the refactor we did without us having to do it manually. We still need to change the way we write everything, but it's gonna help. There's new native container types. There's gonna be a native array, native hash map. Guys working on Dreadnought, they already have this in 2017.3. It's gonna help a lot with the garbage collection situation because there's no garbage collection here. We allocate and release everything manually. There's gonna be a new job system where we can specify compute-intensive tasks in terms of array and transformations that happen of those arrays, and Unity is gonna take care of automatically dispatching threads to process that array in parallel and joining all the threads at the end. And where we're finally getting late into 2018, hopefully, is a new job compiler that once we write our jobs using the new job system, instead of going down to IL2CPP, it's gonna bypass IL2CPP altogether and compile our jobs into LLVM bytecode, and that LLVM bytecode is going to get rid of all the array bounds check. It's going to get rid of all the inlining. I'm sorry, it's going to do all the inlining. It's going to get rid of all the not inlining. It's going to inline everything. It's going to do auto vectorization. So it's going to be a great performance increase. So what can we conclude from here? Data-oriented programming, it's a thing, and I don't want you guys to think that it's a replacement for object-oriented programming. The idea is that it's a complementary approach. Data-oriented is good for stuff that is in the hot path. So everything we call from the update loop, the update function that it needs to walk through a big array of data or objects, these are all candidates to slow down, take a step back, and rewrite them in terms of the CPU cache. But object-oriented programming is still very suitable for everything else, really. Gameplay, non-deterministic code, stuff that is bookkeeping, once in a while tasks, you know, and tools that need to run in the editor and they don't need necessarily to be performance critical. All this stuff, object-oriented programming is still the way to go. So a couple of takeaways from here. Cache is king. It's not like, there's no way to emphasize that enough. Really, cache-oriented programming should be the way that you write all the code if you want it to be fast. And unfortunately, object-oriented programming is not cache-friendly. A couple of things that were big wins were pre-allocating all the necessary memory and keeping the hot data packed tight and alone, separate from all the cold data, so we can make a better use of the cache. Data-oriented is performant, and it's also the future of Unity, for some definition of future next year or 2 years down the road. And data-oriented means that we start thinking in terms of data instead of nouns. So this is the biggest point that I want to make. So we blazed through this. We're at 50 minutes, so it's way faster than yesterday. So instead of going to questions, we're gonna do a pop quiz. Oh. See if you guys were paying attention.
I don't know how to win the crowd over on.
If you remember the algorithms, hopefully you're paying attention, you remember all that code. I want to ask you, what was or what were the order of complexity or big O notation for the position update algorithms? And are they all the same? What do you guys think?
Here, we could see all of
it. No, I don't want to go back. All right, let's think about it this way. What are we doing? We're walking the list of soldiers, right? You got it, Ryan?
There's the big O of n because it's a linear transaction, right?
Exactly. It's O(n), right? All of them are O(n). N is the number of soldiers, and you can see, if you remember from the benchmarks, as the time that it takes to process something, it's linear with the number of soldiers that we have. So they're all O(n). So as a follow-up question, so if they're all O(n), why do we have different numbers if n is always the same?
Constant is different.
Hmm?
The constant is different.
Right?
The number of function calls you were making per soldier is changing.
So to rephrase a little bit, even though everything is the same big O notation, we have bigger big O's and smaller big O's in terms of how long it takes to run code, right? And this is the concept of efficiency and performance. Efficiency and performance are effectively, according to some authors, different concepts. Efficiency has to do with not doing more work than we actually have to in order to solve a given task. So this means that if we can sort a container and we use quicksort, we know that we can get away with it with only n log n comparisons. Whereas if we go to something like a bubble sort, it's going to take us n squared, right? So this is inefficient. The efficient way of sorting would be quicksort. But performance is something else. Performance has to do with how fast our code is running, independently of the complexity of being efficient, right? So to keep on extending on this example, quicksort might be faster, but remember the way quicksort works is that we have to split the array and we need to separate it into two arrays and get all the elements that are smaller than the pivot into one of the arrays and all the others that are larger into another one, and we keep doing this recursively. Now, this is very, very memory hungry, and this is something that is allocating effectively. If we take a look at bubble sort is n squared, but everything is in place on the same array. So it's much more cache efficient. So for a low n, it turns out that bubble sort will always beat quicksort. And even though they are more efficient, right? So efficiency and performance are different concepts. I had a reference, number 9 in the reference slide to a talk by Chandler Carruth, who's a performance engineer at Google, and it's super interesting. All right, and second question. Why was the packed implementation only marginally better than the OOP one on device, but significantly better on the Mac? So you should be able to answer this. I gave you clues through the presentation. Yeah.
Hash line read?
Sorry?
Hash line read? The amount.
Let's assume they're both 64 bytes.
Okay.
But you're on the right track.
Discrepancy between the ratio of CPU to RAM.
Because jump memory jumps then?
Mono is
The cache
virtualized.
The cache size, yeah. Exactly. If you remember all the way back to
yeah.
the synthetic benchmark slide, the quad-core has 432 kilobyte L1 cache, whereas the phone has 264 kilobyte. I think that this actually influenced my results a lot because my synthetic benchmark, I didn't really have a game. You guys are disappointed, but I really didn't really have a game. I just built this so I could measure it. And I allocated all the objects at the same time linearly. So they were still, even though there was indirection, they were all sitting together in memory. So on the phone, we got good results because of the large cache, even though the objects, they end up being together. And because the cache is effectively twice the size, I could hold on to more of these in the cache at the same time. But you can see that as soon as I reduce the number of my structure, we get a huge win on the mobile device. Yeah, and so with that, that is all I have. Here's lots of references. The Unity ones are amazing. You guys, if you have some time to check it out, definitely recommend. Of course, everything that has to do with performance, we start getting into C++ land. So these 4 presentations here are all from C++ conferences, in particular CPPCon. And one thing I want to point out is how this topic is seemingly coming up every year, like of the conference, because it's really the way to go for performance. And even if we're not doing C++, there are great resources to start thinking about cache and performance in particular. All right, so now we have about 6 minutes for questions. And other than that, I want to thank you for taking time to come and hear me ramble about this stuff for 1 hour. Please.
I think it's important when structuring your methods that you also think about where your data is going to be in the cache when you need it. So for example, a lot of times you'll see that you write a function and you have a bunch of parameters, and then you take your local variables and you assign those parameters to them. And then way down at the bottom of the method, after you've done a whole bunch of other things, you access those. Those are no longer in the cache. When you've made them up here, they're in the cache. When they're way down here, they may not be. So making sure that you allocate your variables right before you use them in a for loop, for example, is a lot better to prevent cache misses and things like that.
Yeah, there's definitely, as soon as you start coding this way, I've been doing it here, and I've been doing it in my free time too. This will change the way you write code, and you start going a little bit insane as you try to tie everything together and say, well, I want to make the order of my members in the struct to be like so, but if you change the order, then you can even get performance increases just from keeping the data even closer together in terms of what you're reading at the same time, right? So that is super important. Another thing I didn't mention, but it's related to this, member ordering inside the struct is super important.
Yeah.
You guys, I would definitely recommend start thinking about it. And I think we do it for the most part. It's really difficult to get this wrong, but most data types are about 4 bytes, a float, an int, an unsigned int. But as soon as we start having like Boolean types, or we have like any like struct inside another struct, that kind of situations can leave holes inside the structure because everything needs to be 4-byte aligned when we're reading. So what the compiler will do, if it sees a bool in the middle of your struct, it will pad it with 3 bytes. Those 3 bytes are not accessible to us. We can't do anything with it, but because the read needs to be aligned to 4 bytes, it's just putting garbage in there. And then when we're iterating our list of structs, we're reading in that garbage for the padding just so the memory read could be aligned. A non-aligned memory read is super slow. We need to effectively do a memcpy, so it's a problem. So usually the rule of thumb is organize your data, your structures and your classes and everything that is a grouping from larger to smaller if things are, the sizes are divisible by 4. Keep everything together and just leave all the odd one outs in the end so you minimize the padding that you have. I asked Unity about this and they don't do member reordering. I don't think C++ does it either. So you're just wasting cache because of the order you define your stuff.
It's kind of like a hybrid approach, right? Like when you're saying you can read in 1.6 soldiers, if you had the hot data up top, and in theory it's in that first 0.6, so you're reading in 2 soldiers of accessible data at a time versus 1 every time, and then the 0.6 is wasted.
The problem with this is that you would still, because you're reading 64 bytes because of the cache line size, you're also bringing all the data into your cache. Okay. You won't just read the beginning of it. It will bring everything together, right? So you have this stuff interleaved between the data that you care about. Yeah.
Following up on that concept, though, of having like since you were talking a little bit earlier about object-oriented programming who solves most problems, you can still have, and these hotline caches are better for other types of operations. How do you feel about a hybrid approach in which you have that hot data stored as part of a struct, and when you're doing your update loops, basically what you've done is you can preload those things from that soldier reference and just utilize those, and therefore guarantee that your cache hit is only of the size that you need, and the rest of it's grouped with the rest of the soldier data, but the only expense that you have is that initial read on the objects to be able to load the cache with who is currently moving.
Yeah, definitely, 100%. We don't necessarily need to hold up all our data like this all the time. We can still have our data formatted some other way and then preload of this as we're doing the read. So unfortunately, according to Unity, that initial read from C# will kind of throw the results a little bit, and we'll only get like a marginal gain. So that's why they're developing the new entity component system. So that initial collection is way easier for them in the runtime. But yeah, definitely that's a way to do it.
I did have a second question as well, though, and you were talking about how IL2CPP does not help us in the context of being able to
Inline and auto vectorize, yeah.
Yeah, right, in terms of auto vectoring. And you mentioned it was something along the lines of the data that was, the code that was being generated through machine by converting to C++ was terrible code.
Yeah. This is
what-
Unity's words, but yeah.
So, okay, I wasn't sure if you knew the context to why it was that the compiler optimizations are not reading the things that are specific to that C code.
Yes,
the
it's because it's
go-tos.
go-tos everywhere.
Yeah, the go-tos everywhere that are located on that one.
Yeah.
Is there any, did they give a reason as to why their compiler could not be taking a look at the fact that they're doing all of these memory jumps and try to reorganize or optimize that data in line within the compiler?
Yeah, we didn't ask them about this, but I think I can give you a competent answer, and that is that they don't really compile the C# into C++. What they do is they compile all the C# into MSIL bytecode, which doesn't have for loops, it's just jumps. And then they decompile the bytecode into C++.
Okay, so basically it's the fact that they're doing the jumps from code that cannot access those types of data structures.
Right,
So you're
because-
not able to extrapolate out the jumps to for loops.
Once you're down in bytecode, you lost all your for loops, you lost your function calls, probably. I'm not sure, so 100% sure about that one, but you lost data, right? That's why it's not compiled. It's not called a compilation. It's not called a compiler. It's called a transpiler. The idea of the transpiler is you go to a lower level language and then you go back to a higher level language. Yeah.
Okay.
Great.
So if what you suspect is true, what's the point of ILCPP or whatever it's called?
So the original reason they did it is because the mono runtime is 32 bits.
Right.
And Apple has this requirement that you can't submit anything to the App Store that's 32 bits anymore. You have to be 64 bits. This is the reason they kind of fast-tracked that. So Apple wouldn't reject all Unity games from the store outright because they were 32-bit. So that is, I think that was the main reason. And that's why the IL2CPP implementation for Android has taken longer, because they put all the resources into getting the iOS compiler, transpiler version working first. In terms of performance, doesn't necessarily need to be faster just because it's C++. And in fact, from everything we've talked today, it's funny because being 64 bits is actually worse for your cache, right? Because all your pointers are now 8 bytes instead of 8. So every time you're reading a pointer, you're throwing away cache. You're reading a larger variable. So 64-bit doesn't necessarily mean that something is faster. It's an interesting conclusion that comes from this. Yanni, do you have a question?
You just answered my question.
Okay.
That's exactly the question I was going to ask about padding them. Should they be bigger to smaller or smaller to bigger?
It kind of depends.
Cool.
You suggest this approach for
I mean, like if you have a
data that is used in multiple locations in terms of, like, because from what you're showing, it's more, I almost don't consider it as much as what you're presenting more as data oriented versus being task oriented, right? Similar to just like multi-threading in terms of where you're trying to parallelize as many tasks, trying to optimize the packing of the data for running through that sort of stuff. So, for instance, would you suggest, would there be a way to work with this type of system when you need, say, that movement can occur in 2 or 3 different tasks, let's say?
So I think it really comes down to what you're trying to implement. If you can reuse this data structure to do other stuff that you need to do in your game, some other task, then by all means. Otherwise, you can always do what Brian was saying of you have a specific data structure for that case. You have to profile it to make sure that it makes sense. But then have another representation. Maybe you don't need the destination or you don't need the speed because you're doing AI and you're just trying to look where things are going, whatever reason it is. And in that case, you could have another data structure for that and just load it in the beginning of your frame instead of jumping around memory, just kind of doing it once. Hopefully that makes sense. Otherwise, we can discuss offline if there's any other specific case. But yeah, as long as you can reuse it for sure. Otherwise, you will end up with a program that has all these. Everything is modeled after what data you need to transform and the system that needs to that effectively transforms that data, right? So if you can reuse it, great, but if you can't, then you end up with some duplication, and that is not the end of the world. You get performance gains. Again, we kind of break a little bit with all the dogma of object-oriented programming, and we move on to something that is more cache-friendly.
It's just that also has its own, we just have to remember that it also has its own set of problems
Yeah.
that we need to deal with.
Yeah, that's why it's super important to benchmark all of this. And I was actually surprised when I saw that the phone version was barely any faster than the other one. I was thinking, well, all my theoretical knowledge about the subject and the results from the Mac tell me it should be like way faster, right? And when I profile, it's like, well, if this is the only thing I'm gonna do, we don't even need to bother about it. So it's super important to profile.
So I wanted to ask about that. You increased the efficiency in terms of the number of cache lookups by like 5x.
The performance, yes.
Roughly. The performance, but we saw like a 10% improvement in the runtime. So do you think that the cache reads weren't the primary limiting factor for work, or like what's your read on that?
My theory, if I understand the question correctly, my theory is that the larger, there were two things. The fact that it was a completely synthetic benchmark and I was allocating the 10,000 objects all at the same time in a for loop made sure that everything ended up together in the heap, even though in real life, in a real game, we would have all these other extraneous objects interleaved in memory, right? That arrow, the VFX, the coroutine, everything that happened in between soldiers being created. So I think in practice, we would have seen a better result there. And the other thing is because of the larger cache size, I think that helped mask the inefficiency in that approach. I consider it like a failure in the benchmark rather than like a rule of it's not worth it to do this. I think it still might be worth it, but it needs to be profiled.
So my other question is with lists, because maybe I've just been reading the documentation wrong my whole time, but I thought the lists was supposed to be a contiguous memory allocation as needed to accommodate whatever size it's supposed to have.
Yeah, so it depends on the list implementation. I'm not sure which one it is.
In terms of the mono one, I guess.
Yeah, I don't know how that list is implemented underneath. Hopefully it is an array, what Java calls an array list, which is continuous. Hopefully it is that, because we have a lot of code that assumes that is the case. In C++, the standard list is just a double linked list, so that one you're for sure jumping around memory. But what's important is that when you have a reference type, even though all those pointers are together, they're pointing to places far out in memory, right? So the problem you're having is not from jumping from the first element to the second and the third. Those are all together in memory in any case. But they're not the objects. They're pointers to objects that could be anywhere in memory. So you're jumping all around the place, even though all your pointers are stored together, the things they point to are spread, and you need to fetch those in order to read the data on them. So that's the biggest difference.
Well, that's the assumption that the list is
the list is holding a reference type.
Yes.
If the list were holding a value type and the list implementation is everything's packed together, then yes, you can use the list itself using an array. Yes. All right. Any other questions? We're a little over. So again, if you want to discuss anymore, I can talk about this for hours and hours and bore you to death.
This is more tangential, so it doesn't matter.
Yeah.
But, you did explain boxing and unboxing.
Oh. Yeah. Boxing is whenever you have a value type and you're trying to put it into something that is generic, something that is effectively object type. So you're going from a narrow type to a narrow data type to something that is a reference. What happens is that the object gets put into, the value gets put into an object, and that is the concept of boxing. It's when you have, for instance, a float, and you're saying, I want to store this float as type object. Then when that happens, object cannot really hold on to a value type reference. So what happens is that a new generic object is created, the value is put in there, and then that's called boxing. And then when you cast that from the object type to a float, that is the unboxing process. And hopefully that makes sense. It is not for free. It's allocating GC memory, it's doing a copy. It's a problem. You can see this if anywhere in the code you have stuff like a dictionary of string as the keys and object as a type, like some JSON frameworks do. Every time you store a float in there or an integer in there, all those, they can't be stored in there because of the language doesn't allow that. So all those are put into a new object that lives in the heap. It has a copy of the value, and every time you cast them out of the key, you're paying for that conversion, which is reading that value, getting the object from memory, reading the value, putting it into a value type. So it's pretty inefficient. So yeah, we should avoid boxing. It's significant enough that if we profile the game and the game has enough boxing and unboxing, it will come through in instruments of one of the top CPU offenders. It will beat other stuff. It will be up there with like rendering and animation. Yeah, should avoid boxing and unboxing.